One of those days, so better late than never. Okay, so let's look at this question. So we have a 12 volt power supply. So E or VT, total voltage, is 12. We have 3 resistors of 15 ohm, 12 ohm, 36 ohms. And we have this resistor in series with the two of these who are in parallel. You know from earlier that the total resistance of these two resistors should be less than 12 ohms because there are more gaps. And you saw that in the cartoon Guide to Physics. Okay, so part 1. Calculate the total resistance. Now remember, for Ohm's law, so here we're going to use Ohm's law for all the circuit. So we can use Ohm's law for a part of the circuit or for all the circuit. So in this case, we're looking for the total current. So the total current is going to be the total voltage over the total resistance. Okay, so the total, now to do that, we need to get the resistance, the total resistance. So we'll do this over here. So first of all, we'll get the resistors in parallel to get an effective resistance. 1 over R total is 1 over R1 plus 1 over R2. You've derived this, but you're going to use it now. So we know the answer is going to be less than 12. Okay, we're still a bit confused by that, but we're getting there. Of course you're not confused. It's as clear as day. So we have a common denominator here, it's 36, so 3 plus 1. So 1 over R is 4 over 36. R is 36 over 4, which beautifully comes out to be a nice whole number. R is 9 ohms. So the total resistance in the circuit, R1 plus R2, is 15 plus 9, which is 24 ohms. Okay, so that's the resistance of the circuit. That's going to be very important. Right, so the total current now, we're in business. The total voltage is the EMF, which is 12. Total resistance is 24. So the total current in that circuit is 0.5 of an amp. Okay, and we're happy with that, 0.5 of an amp. Okay, so that's fine. So that would be the current here. Okay, I'll just put it in here. Now you're aware, look, it's 0.5 going through this. Gets to here, it's going to split. So it's going to split. Some is going to be less than 0.5 way up here, less going up here. There's going to be more current go up the top, 3 times more current because the ratio is 1:3. And more current will flow through the smaller resistor because it has a bit of copper on. Okay, part 2. The total current. Okay, sorry, I've done part 1 and part 2 together. My mistake. So that's part 1 and this is part 2. So read the question. Okay, part 3. The current passing through the 12 ohm resistor. Now this is the ratio. Okay, so the 0.5 amp splits in ratio 12 to 36, which is 1:3. Okay, so basically 1/4 and 3/4. Probably the easiest thing to do is in fractions. So 3/4 goes through the 12 ohm resistor. So 3/4 passes through smaller 12 ohm resistor. There's many ways of doing ratios. I like to do a fraction. Okay, so 3/4 of 0.5. Okay, so that's 0.375 amps is the current through the 12 ohm resistor, and you normally write it like that, current subscript 12. Ratios make that a lot easier. You could also do that using Ohm's law for that part of the circuit. I'd always be inclined to use ratios when I can. Ratios are our friends. Okay, right. Okay, I'm just going to move this up a bit. We know that's 12 volts up the top. Okay, part 4. The potential difference across the 15 ohm resistor. Now, this is part, so Ohm's law, part of a circuit. Okay, so we have V is equal to IR, just for that part of the circuit. So, the 15 ohm resistor, we're looking for the potential difference. The current going through it is 0.5, because all the current goes through it. The resistance in this part of the circuit, I'm going to just put it, look. That's the part of the circuit we're interested in. So we want the voltage across that part, we want the current going through it, which is 0.5, and we want the resistance in it, which is 15. So the voltage we're getting here is 7.5 volts. Okay, that's it. So up here with an example of using Ohm's law for the whole circuit. So total current, total voltage, total resistance. Down here we're using Ohm's law for parts of the circuit. The part is within the dotted line there. Okay, we can use Ohm's law twice. It's just wonderful, Ohm's law. Okay, Part 5, the potential at x. Now this is new, okay? I forgot to put this in earlier, so you're going to go to your definition sheet and you're going to write this down. So potential at a point. It's important now into your definition sheet. Okay, is the potential difference between that point and Earth. Remember, Earth is 0 volts. Okay, so that's the potential. Right, so let's look at what does this mean for this scenario. So let's look up here. And this certainly makes things a little more sensible why it's called potential difference. Okay, you have a potential here of difference of 7.5 volts. So you've used 7.5 volts of energy. So think about it. Coming in here, you've used nothing. So the potential there is still 12 volts. At this point, you've used 7.5. The potential difference in this point and this point is 7.5. So by subtraction, hopefully you can see that the potential at that point is 3.5. Potential difference, remember difference means subtraction, is the difference in the potential between here and here, which is 7.5. So if we subtract it correctly, we'll be fine. Okay, so it's 4.5, isn't it? Okay, 4.5. It's been a long day, so 4.5 volts. Right, so it's potential, and the way you write this is potential at x. So potential at x is 4.5 volts. Now, if you were doing this in an experiment, you'd connect this point here, not to the other side of the resistor. You'd connect it to the earth. Now, the earth is 0 volts, which would effectively be connecting it to the minus of the power supply. Because remember, this is 12 volts. This is 0 volts. So think about potential. You have 12 volts. You still have 12 volts of energy because you haven't used any energy because there's no resistance in the cell, in the wire. You use 7.5 volts here, so you're down to 4.5 volts. You have 4.5 volts left. You use all that 4.5 volts going across here, and you're back to 0. Okay, so you get the idea of potential. It takes a while. We get the idea of it. Okay. Part 6, the potential difference across the 12 ohm resistor. Well, we have many ways of doing this, but let's think of ratios or Kirchhoff's law. Okay, we've 12 volts here. The potential difference we've used is 7.5 volts. So clearly, rather than having to use Ohm's law, which we could use for that part of the circuit, you can just do it by subtraction. And this will be relevant to your assignment tomorrow. 12 volts minus 7.5 volts. So the potential difference across the 12 ohm resistor is 4.5 volts, which is the same as the potential because you're effectively measuring the same thing. Okay, don't be concerned. Okay, you may be saying, okay, that's the potential difference across the 12 ohm. What about the 36 ohm? It's the same potential difference. Think about it. If you connect your leads here or connect them here, you're going to get the same value. So that's 4.5 volts. There you go. This is definitely one that's worth looking at again. Okay, and when you do your assignment tomorrow, you'll start getting the hang of it. Okay, let's get clear. When we come back in September, we'll be doing a day or two of a load of these. So if we get the hang of it at all at the moment, we'll be very happy. Very good.